Hello students, welcome to Inside Physics. Today we will see what is an atomic spectra. This is a topic related to the topic atoms. So here atomic spectra, it is the light emitted or absorbed by a particular element. It is the characteristic of that element. That particular spectrum, that means emitted lines or absorbed lines, will have a peculiar wavelength only related to that particular element. That is called atomic spectra. It is also called characteristic atomic spectra. For example, if you take an atomic gas like hydrogen or any other vapor, it is electrified under very low pressures, so that the gas will be emitting some radiation. Okay, so this radiation is the characteristic of that particular element. This is called line spectrum. Line spectrum is because of the emission of the some radiation by a particular element when it is actually given some high electric field, the high potential subjected to high potential difference under very low pressures, some gases will emit some radiations. This is on the dark background. You can see some bright lines, which is called a line spectrum. At the same time, if the white light is passed through the atomic gas, so the white light is absorbed by the gas and the dark lines are formed, which is called absorption spectrum, which you can observe through a spectrometer. Okay, the spectrometer gives the wavelength, the data analysis by the spectrometer gives the wavelength of that particular absorption spectrum, and the lines which are shown as bright lines on the dark background, which is having some wavelengths, is exactly matching with the absorption spectrum, which are dark lines on the bright background in the reverse. So the line which is emitted in the line spectrum exactly matches with the dark line which is in the absorption spectrum. So the wavelength is same for a line in a line spectrum and for a dark line in the absorption spectrum. So by this, what you can say is that this atomic spectra is like a fingerprint to identify that particular element. So if you want to identify something in these days, we will thumb it in some characteristics. The person who is need to be identified, we will thumb and we will identify the fingerprint in some cases in any of our solutions to the in government sector or something like that. Okay, so here also the spectrum, which is called atomic spectrum, a line spectrum or absorption spectrum, is a fingerprint to identify the element. And now we consider the hydrogen, the series of spectral lines. The spectrum is divided into series. What is a series? Here we call it as spectral series. A series as a set of lines which is in line spectrum or in absorption spectrum, emission or absorption spectrum. These spectral series are a set of lines. So while doing some experiments on hydrogen gas, scientist called Balmer has identified some characteristic spectral lines which are emitted by the hydrogen gas in the visible region. He observed the characteristic spectrum in the visible region. Visible region, you know what is the visible region of the eye? 450 nanometers to around 800 nanometers is the visible region. In that region only we can see the wavelengths. other are invisible regions. So Balmer, on his observations on the hydrogen spectrum, has observed some characteristic lines which are in the visible region. So to calculate the wavelength of that spectral lines, he has given a simple empirical formula to calculate the wavelengths. Here you can see the Balmer series. This is the spectral series. Series is nothing but a set of lines. This is a series, this is a series, and this is a series. So this identified by Balmer, so it is called as Balmer series. It is named after the scientist, and you can see there is an upper limit and lower limit in a particular series. Highest wavelength, lowest wavelength for every series you can see that. So if we are discussing about Balmer series, look at this. This is 656 nanometers, the highest wavelength, which it belongs to, say, red. See, the wavelength almost appears as red because red is having the highest wavelength. So the second one, here these are the lines, and the lowest wavelength in Balmer series is 365 nanometers. So a series is a set of spectral lines with some highest wavelength to lowest wavelength. This is the limits of the series. And is there any regularity or any symmetry observed in the spectral lines? Means no, there is no regularity, but we can observe one thing here. See, the spacing when you come from left to right or right to left, the spacing between the spectral lines is gradually decreasing or increasing in a systematic way, in a geometrical way. It is increasing or decreasing. You can see that when you are moving from right to left, the spacing between the lines is decreasing in a systematic way. That is, we can observe in the emission or absorption spectrum. So what is the formula Balmer has given to calculate the wavelength of a particular line in the series? He has given as 1 by lambda is equal to r into 1 by 2 square minus 1 by n square. So this is the formula he has given. So here n, what is n? N can be 3, 4, 5, 6 up to infinity. Okay. So here if you put 3 here, 1 by lambda is equal to r into 1 by 2 square by 1 by 3 square. Here r is the Rydberg constant and its value is 1.097 into 10 to the power of 7 per meter. This is the value of Rydberg constant. Okay, so this value lambda, if you calculate, this will come around lambda is equal to 656.3 nanometers, and this is looks in a red color because of this wavelength. So this wavelength is called here as H alpha line by the Balmer. He called this line as H alpha. So this is a simple empirical formula only to calculate the wavelength. This formula doesn't give any other data about the spectrum. So what is the next line? Here if you put 4 in place of n, we will see that. If you put 4 in place of n, so it becomes 4 square. Okay. So this value, if you calculate by replacing Rydberg constant, this value, this lambda will be coming as wavelength of this line will be around 486 nanometers. There may be a point Here wavelength is 486 nanometers will be coming if you calculate that wavelength. Okay, so that 4 which is substituted will give you this value, which is termed as H beta line by the Balmer. So H alpha, H beta, and see, this is H gamma. If you put 5 here, you will get the value of H gamma, which is around 434 nanometers. So like that, the wavelength is decreasing, and the least value in the Balmer series is 364 nanometers. To get that value, you need to put n as infinity. If you put n as infinity, this term here, to get the last spectral line wavelength, that means 364, here you can see 364, you need to put infinity, this term will become 0, and you will get the value here as 364. So this is the simple formula Balmer has given to calculate the wavelengths of different spectral lines. Okay, so the other series, I have written here Lyman series, second one Balmer, Passion series. So the other series are found out by the respective scientists, which are the series were named after after their discoverers. Who are them? The first series was discovered by Lyman, and second one we already discussed, Balmer, and the third one Passion, and the fourth one this bracket, and fifth one P fund series. These are the 5 series that were discovered by the respective scientists. Okay, so these scientists have also followed the same formula which has been given by Balmer. So Lymer, Balmer, Passion, bracket, and fund. So after the last line in a series, what you observe, is there any spectral lines or not? There will not be any particular lines. There is a continuous spectrum, and the intensity is also very low. Even in a series, if you are moving from the highest wavelength to the lowest wavelength, you can also see the spacing between the lines is decreasing, and the intensity is also decreasing, and the spectrum after the least wavelength, there will not be any lines. There is a continuous spectrum with very feeble intensity, very low intensity. So here Lyman series, for Lyman series we can use the same formula given by for Lyman series. 1 by lambda is equal to r into 1 by 1 square minus n square. So for Balmer series we have already discussed. Next, for Passion series, 1 by lambda is equal to r into 1 by 2 square. Here it will be 3 square minus n square. Here n is equal to 2, 3 up to so on. Here n is equal to 4, 5, 6 and so on. Next, Lyman series, Passion series, and next one bracket series. 1 by lambda is equal to r into 1 by 4 square minus 1 by n square. Here n is equal to 5, 6 and so on up to infinity. In the same way, P fund series will be 1 by lambda is equal to Rydberg constant into 1 by 5 square by 1 n square. Here n is equal to 6 comma 7 up to so on. These are the different series and their wavelengths we can calculate by using these formulas. Okay. So here these formulas are useful to calculate the wavelengths of spectral lines. So there is a formula connecting wavelength and frequency. As far as we know, this is the connection between wavelength and frequency. This implies frequency can be written as c by lambda. Okay, so here thus this implies this 1 by lambda is equal to nu by c. Okay, so if you place this 1 by lambda is equal to nu by c, where nu is the frequency of the radiation in the spectrum, this 1 by lambda, if you replace them, then you can get the relation between frequency and the spectral lines. This is the relation, and we need to replace nu by c in place of 1 by lambda. So even in Balmer series also there will be this c is moving to the right hand side. So all in all we can write this frequency wavelength relation as RC to 1 by n1 square minus 1 by n2 square. If you take n1 as 1, n2 will be 2, 3, 4. If you take n1 as 2, n2 will be 3, 4, 5, like that. So this is the relation between frequency and the wavelength. So here this is how we understand the characteristic spectrum, and this empirical formula given by this Balmer is actually does not give any information on the spectrum. Why only some wavelengths, some frequencies are appearing in a particular characteristic spectrum of an element? This formula will not give any information on it. It is only simply a relation which can give you the wavelength of the spectral line, and the interesting one is this characteristic spectrum is very useful in identifying elements and in analyzing elements. So this is about atomic spectra and spectral series. The next video will come with some more interesting topics.